So Matteo, what happened?
I have no idea.
Somebody left one of the hosts left the lecture and closed the meeting.
Maybe that was me, I guess. I don't know. I'm sorry.
Okay. So if you quit the lecture, you don't close the meeting for everybody, you just leave the meeting, okay?
So the entry chime should be deactivated now. I haven't heard it in.
Okay, cool. Okay, so let's start again. Sorry about this. Slight mishap. So where is it? Here. Okay, can you guys see the slides again?
Yes.
Okay. Okay, so why single neurons? Yes, because they're the computation unit of the brain. They constrain network computations. Also, as Giacomo Indiveri explained in the first lecture, one of the interests in the field is also to emulate neural circuits in so-called neuromorphic hardware, which emulates the principle of neural circuits. And the idea is not to reproduce neurons in all their complexity, it's really to capture the principles of their computation in a different hardware. And also, I quickly want to mention, some experimental methods that really are based on an understanding of mechanisms at the single neuron level, which are very important for neuroscience. Okay. Now, with respect to the first point, right, which is understanding the computations that neurons perform, and then how networks of neurons compute, there are really many different approaches to do this, and the two extremes are to essentially try to build biologically realistic simulations of brain circuits. And this is challenging because, as you saw also in the last lecture, there is a lot of diversity across neurons. Like, not only is every neuron by itself very complex, every neuron is different from another, and there are many different types of neurons. And so, creating such biologically realistic simulations is hard from a computational point of view. It's also hard because mostly we don't have all the information to really build a realistic simulation. So some approximations need to be made anyhow. But nonetheless, this is one approach. The other end of the spectrum of how to study neural computation is to try to simplify what single neurons are doing in particular, and then kind of abstract what we think are the most important computations. And that's very much what we will be doing in this lecture. And I just want to mention that if you're interested in the other approach, which is the one to build biologically realistic networks, you can look at the Blue Brain project at EPFL. There are some nice movies on YouTube that you can look at. And there, the original plan, the original goal was to simulate one entire cortical column, or then a series of columns in somatosensory cortex of mice, based on actual reconstructions of neurons. So these are, thousands of neurons that are simulated down to the conductances in the membrane channels, and it's very, very complex and a huge effort. So you can look this up if you're interested. So we're gonna, as I said, use a different approach. Instead of really taking into account the whole complexity of the neurons, we're gonna try to simplify. And there are many, ways you can do this, right? You can pick what level of abstraction you're gonna still use, right? So you can think of, for example, still modeling some aspect of the morphology of dendrites, right? That you have individual branches, you have individual dendrites, coming from this out of the soma. You have the axon, and you kind of model these as compartments, right? That are somewhat separate from each other, but that are linked then by some wires. And you can go further and just say, oh look, we just have individual dendrites, but they don't branch. And then we have the soma, and we have the axon, and you can go all the way to what is called a single compartment model, or a point neuron, where the neuron really is just one sphere essentially, that has one potential, right? And all the inputs come out directly into this point neuron. And clearly, you cannot model everything that real neurons do when you use point neurons. Things like transmission delays, it makes a difference if a synapse enters, here, or if it contacts the neuron in the soma, right? One will have, in one case, the delay will be longer for the current to reach the soma. When you have separate branches that are kind of, computing their own nonlinear operations, then you can have what are called dendritic computations, right? So you have in a way, it's not the computations are not just performed at the soma, but you can also start computing in dendrites. You can have things like back-propagating action potentials in more realistic neurons, right? Where the action potential is generated here at the axon hillock and then mostly propagates down the axon. But in some neurons, actually, the action potential also propagates a little bit back into dendrites, and that there are some models where this is important for learning, for example. So all of these effects, if you look at the point neurons, we can't model, and it's an open question to what extent these kind of effects are generally important and necessary to really capture in the end what networks of neurons are doing. So we're going to start, with these very simple point neuron models in the next lecture. Yes, non-working implementation, you heard a lot already, or some at least in the first lecture. You're going to hear more in the end. Again, the idea is to capture the principles, not all the details. And as I mentioned, experimental procedures, like a lot of the ways that we study the brain, both in how we measure activity and how we perturb activity, really take advantage of these mechanisms that we will be discussing today and in the next two lectures, which are very much happening at the level of single neurons. So that's another practical reason why these are very important in neuroscience. Understanding these mechanisms, even if not all the level of detail, maybe will matter to capture computations of networks. Okay, so the main phenomenon that we'll try to explain today is the so-called resting potential, and really it lies at the foundation of most of what neurons do in terms of computation. And so the basic observation is that if you take an electrode like this one, and here it's outside of the soma, but you can actually push it into the soma, and then you can measure the potential inside the cell, right, compared to the extracellular space. And the basic observation is that if you do this, you find that the intracellular space is hyperpolarized compared to the extracellular space, right? So it lies at a somewhat lower electrical potential. So what it means, right, if you put a wire, say, between the inside of the cell and the outside, you would have current flowing between the two. And this is something that you don't only observe in neurons, actually. It's something that many cell types show in the body, so that you have an electrical potential between the inside and the outside. And so we'll discuss in some detail about how that comes about. But the main reason why neurons and other cells are doing it, it's a way to store energy, right? And so one analogy which works mostly, it's not a perfect analogy, is that something like a storage power plant, right, where you take water from down here at 0 meters, you pump it up higher, and now you have a reservoir, and this reservoir now is potential energy that you can use if you let the water down again the pipes to produce energy. Okay, and something similar is what is happening in neurons. They're maintaining this difference in potential. They put in energy to maintain this difference in potential, in the same way as you a storage power plant, you have to put in energy to first pump the water up. But then once you have done this, you have this energy available quickly if you need it. And so, again, the analogy works with the pumps to some extent, because the main ingredients to generate these resting potentials are the following. So you have the cell membrane, right, which is just a barrier between the inside and the outside of the cell, and usually, so it mostly blocks diffusion of particles between the inside and the outside. The other thing you have are indeed pumps. They don't pump water, but they pump ions, and so they pump some types of ions, like sodium, from inside to outside, and others like potassium from the outside to the inside of the cell. And what that does, it creates differences in concentrations, right? You have, for example, potassium is enriched inside, and sodium is enriched outside. But now there's an additional element that will create the resting potential, which is ionic channels. Okay, so you have, whereas most of the membrane particles cannot diffuse through, you have these specialized proteins, which are called channels, that actually are conductive for ions, but they are selective. So you have, for example, some channels that are mostly selective for sodium, so they only let sodium particles through, and others that are selective for potassium. Okay, so this is really not something that one can describe so well in this analogy of the water and the storage pump, but we'll discuss how these three ingredients together create the resting potential. Okay, and so I find it useful to go through a kind of a thought experiment, which, if you get it, it's imperfect. Okay, it's not a perfect replica of what happens in neurons or in cells, but it kind of gives the basic idea. So imagine that you have a container, this sphere, that contains some, let's say that these are gas particles. Okay, you have the boundary of the container, which is our membrane. There is some temperature in the system, so there is thermal motion. These particles move around, and there is, let's say that for simplicity, this container here, the inside, is actually inside this bigger volume, which we call the outside. Okay, and now we have set up a situation where at time 0 there is this concentration gradient. Okay, so this substance X, there's more of it in the inside of this container. And now there are these channels through which this particle X can exit. And the question is, what happens, right, if we open the channels, say at time 0, what happens if we just wait, okay? And specifically, will the concentration, which we indicate by these brackets, inside be larger than outside? Will it be the same, or will it be smaller inside than outside? Okay, so if we had time, I would now, I guess, poll you and ask to raise your hands and say what you think the answer is. But based on last year's lectures, most people will correctly say that at equilibrium, right, if we wait long enough, the concentration inside will be the same as the concentration outside. And this is microscopically, there's a lot of change happening, right? You have some of these particles go in, some go out, but overall, the concentration will be the same. So at the macroscopic level, there is no change. You have reached a steady state, okay? And I will make this a bit more complex. Now we'll assume that we have not one type of particle, but we have two types. We have positively charged ions and negatively charged. Everything is the same as before, so we only have them at the beginning inside this volume. And we again have channels, but now the critical difference, or the critical property of these channels is they're selective only for one type, say the plus type, okay? So the minus particles, they can actually not go anywhere. They can not exit this inside space, whereas the plus particles, they can go through these channels from inside to outside and from outside to inside. And again, we have set up the situation where we have a concentration gradient, right? So we have more plus particles inside than outside, actually none right now outside. But we have done this in such a way that there is actually no net charge right now, right? So we have equal numbers of positive and negative particles. And in fact, what will happen, right, in these situations, you can imagine that these will kind of pair up, right? Again, these are moving around. You can think of it as, again, as a gas. But, positive and negative charges will kind of try to pair up. And now we ask the same question. Okay, so what happens if we open these channels at time 0 and just wait until a steady state is reached? And again, these are the possibilities. And since we're short on time, I'm going to give you the answer. You can try to think this through as an exercise, I guess, afterwards. The answer is that unlike in the previous case, right, where we had at equilibrium that the concentrations of the particles inside and outside was the same, now we will reach an equilibrium where the charge of this the concentration of the plus particles inside is larger than outside. And the reason is that whenever one of these plus particles, right, leaves the inside of the cell, it leaves behind a negative charge, okay? So slowly, this inside is starting to get negatively charged, right? It's not true anymore that you have equal positive and negative charges inside. So you have, as soon as some positive particles leave, this will get negatively charged. And so it will become attractive for these positive ions, okay? And so it will get, harder and harder for the positive charge ions to leave the inside because they are attracted to it, where it's still very easy for them to go, from the outside to the inside. And so what that means is that you will reach this equilibrium with the concentrations of the plus particles larger inside than outside, okay? And, as before, these positive and negative charges that now were separated in this process, they will try to find each other. And so this excess charge will tend to accumulate on the surface of the membrane, on the inside and the outside. Okay, and because we have an excess negative charge now inside compared to outside, the potential is lower inside than outside, and this will be the equivalent of the resting potential. Okay. So again, this is it's really a thought experiment. There are many things, I'm sure, holes that one can poke into this, but I think it's still conceptually useful to go through this. And clearly, things are more complicated in neurons, though, because even though we have these basic elements again, right? So we now do have positively and negative charged ions that are floating around in the intracellular and extracellular space. We again have the barrier. We have channels that I'll show in a second. And we have concentration gradients, right? Like before, we started from a setting where there were more plus particles inside compared to outside. So we have this situation, again, because there are these ionic pumps that are actively moving ionic type ions between the inside and outside, right? And so you tend to have, as I said, more potassium inside, and sodium, calcium, and chloride are enriched outside, okay? And if we look at now again at the equilibrium, right? If you just look at a neuron when nothing is happening, if you look at the membrane potential, so you measure potential across the membrane, right? You have a constant potential inside. That's because here essentially you have a conductor, right? So inside a conductor, you don't have changes in potential. Then the membrane, which separates the inside from the outside and is also an electrical insulator, there you have now a gradient, a change in potential, and then outside you are at zero, right? So this difference, as I said, is about 60 to 70 millivolts. And just to give you an idea, you know, of microscopically what this looks like. So if you take 1 cubic micrometer of cytoplasm, right, which is a substance in cells, out of cells, you have about these quantities of different types of molecules, right? So these ions are the ones, or some of these 10 to the 8 ions are the ones that are going to be moving inside and outside and creating the potential differences. But you have other kinds of molecules as well. These numbers will be important later on, but not so much right now. Okay, and you know, the other thing missing from that picture that I showed you are these channels, right? Which again are selective, and in terms electrically, they have a large conductance, right? So the conductance, which we indicate by G, for one of these channels is about 10 to the 4th times the conductance that you would have through the membrane, okay? And many of them are selective for one or just a few ion types. And what that means is that, say, for any 10 to the 4th, say, ions of the right type, there is one of the wrong type that makes it through. Okay, so they're very, very selective. And really, in the end, many computations that neurons will perform will result from having these channels, right? So from the fact that channels are selective for a specific ion type, and also by the neurons will be able to compute by changing these conductances, right? And changing the conductance will be achieved either through neurotransmitters at the synapses, you hear a lot about this, by changes in voltage themselves, so you can have, this is how the action potential will be generated, or yet other molecules, okay? But the basic idea is that you have these channels, they're selective, and they change, they can change their conductance, and that's how computations arise. Okay, now, yeah, so I guess we're gonna run a little bit late, and then we're gonna have a shorter break, but I wanna at least set up this basic derivation now of the resting potential, right? So what we would like to obtain is essentially an equation, right, that tells us what this resting potential is, right? And so, and what kind of parameters, right, what factors affect the resting potential? Yes?
Later, there is a question.
I cannot hear you, you're muted.
Yeah, there is a question asking, what do you mean by conductance in this context, like the current conductance?
This conductance. Yes, so the conductance is a measure of, right, that you encounter when you describe electrical circuits, right? It describes how much current flows through an electrical element given a potential difference across it, right? So the conductance is 1 over the resistance of that electric element. So what it says in this case is, given a certain potential difference between the inside and the outside, how many ions will flow through the channel or comparatively will flow through the membrane at any given, within a second, okay, within any given unit of time. And in this case, again, the conductance through the channels is much higher than through the membrane. Okay, so as I said, we want to now derive an equation or get an understanding of what are the different factors that affect this resting potential, okay? And so we'll think about this with a concrete example, right? As I told you before, there are actually many ion types that have these concentration gradients, and they come with their own channels associated with them that are only selective for that particular ion type. And so we're going to start by just considering one of these ion types and channels that are selective for that ion type. For example, potassium, okay, which is enriched inside compared to outside. And what I drew here is something like the equilibrium situation, right? Where we know that the concentration inside is larger than outside, and we also know that there is this potential difference between the inside and the outside. And so how are we going to derive now this resting potential of minus 70 millivolt? So what we're going to do is we're going to try to write equations that describe the flux, right? The number of ions per unit time that move from the inside to the outside. And then an equation, a similar one, that describes the flux from outside to inside. And essentially, we will reach an equilibrium, right? When these fluxes are the same, okay? So the equilibrium is going to be given by the setting where the flux out to in is equal to the flux in to out. And so we just need to find expressions for these. And so this is another place in the lecture where it would be nice to actually, slow down a bit and just think for a second about what, if we write down equations here, what could even affect these fluxes, right? And I really encourage you to spend some time thinking about this after the lecture. Now, because we're late, I'm again going to tell you the answer, okay? But if you think about it, just intuitively, things that will make a difference are, again, what is the conductance of these channels, right? If you have bigger channels, it might be easier to go through, right? Clearly, the number of channels, right? If you have one channel across the entire membrane, it's going to be different than if you have 10, right? So if you look at the overall flux through the membrane. And so you have a number of parameters or variables that you can think of that will affect this flux, that we will essentially summarize in this parameter gamma, okay? Which we actually don't know, but it turns out that maybe we don't need to know it to derive the resting potential. But the one thing that clearly will also have an effect is the concentration, right? You can imagine that if everything stays the same, all things being equal, the number of channels, the type of channels, and so on, if you double the number of ions inside, then twice as many within a given unit of time will make it through the membrane, okay? And so that would mean that the flux, for example, from outside to inside, actually, so I drew this, I was discussing this one, so it doesn't matter, it will be the same from inside to outside, is proportional, in this case, to the concentration outside, right? And that makes intuitive sense. And the one thing that doesn't appear, just hold on one second. So the one thing that doesn't appear here in this equation, interestingly, is the potential, okay? And the reason that the potential doesn't appear is that once a particle makes it to the entrance of the channel, right, it starts feeling this potential. So essentially it gets now attracted over to the other side, right? And then it just moves to the other side. So that's why potential actually doesn't appear in this specific equation describing the flux from outside to inside. Okay, I think there was a question, Vanessa.
Yeah, so the question is, when a positive ion pairs with a negative ion, does it make less likely to the ion to pass through the channel?
Yeah, so again, this is a very dynamic process, right? And so they do pair up, and the excess charge tends to accumulate here. What will happen, so in this case, in this direction, it wouldn't make a difference necessarily, because as long as you reach the entrance, more or less, you're going to make it through. But I agree, actually, probably it would make a difference if it's paired up, because it won't feel the attraction from the other side. But we're going to see past all of these details, right? And in fact, we're going to, this is a very simple expression, right? Essentially, the only parameter that matters is the concentration, right? So clearly, this will be a simplification, but it turns out that it works experimentally pretty well. And now the expression for the flux inside to outside, we're going to make, one important assumption, which is that this gamma we'll assume is the same, right? So all of the factors that somehow have to do with how easy it is for the channel, for a particle to reach the entrance of the channel, like on one side or on the other, we're going to assume that they are essentially the same, okay? So clearly not all the ions will make it to the entrance at any given unit of time, but we'll assume that it's the same fraction of the ions that we have, right? So we have, again, the concentration, this time inside, multiplied by this factor gamma. But now there's one big difference between these two fluxes, which is that when a positive particle now reaches the entrance of the channel on this side, on the inside, it actually isn't done yet, right? Because to actually go to the outside, it still needs to make it up, this potential difference, okay? Because it is positively charged and because the potential outside is larger. And so it means that the way it's going to overcome this potential difference is thanks to kinetic energy, right? So just thermal motion, because there is temperature, so these particles are moving, they're bouncing around, and some of them will have enough energy to cross this energy barrier, okay? Which is given by this. I actually can't see my slide here because it's covered, but I think it says Q times V equilibrium, okay? So you need to have enough kinetic energy, and so this will be the probability, right? So the fraction of ions that have enough energy to cross the barrier. So those are the only ones that are contribute to the flux from the inside to the outside. And Q here is just the elementary charge, right? So the charge of an electron, the positive charge. Okay, and we're gonna describe this and factor just, and then we're gonna take a break. So what is this probability, right? This is one thing that we can't derive easily. You can kind of figure out what this must be, right? So it must be that the more you increase the temperature, the more particles bounce around, the more kinetic energy you have. And so this fraction must increase, okay? And also, so temperature has an effect on it. You can also think that, this V equilibrium has an effect, right? So if you have a larger potential, you will need more energy, or to say it differently, for the same temperature, a smaller fraction of particles will have sufficient energy to cross, okay, if V equilibrium is large. And so this is the answer is this one. The general answer, it's called the Boltzmann factor. It's E to the minus the energy that you want to, have, divided by this constant KB. This is a Boltzmann constant times the temperature. And in our specific case here, this energy that we want to overcome is this one, right? It's just charge times the equilibrium potential, which we're trying to cross. And this is how this factor looks like as a function of temperature. So if you look at a particular voltage here, right, you can see that if the temperature is 0, there is no thermal energy, and nothing is moving, so none of the particles has sufficient energy to cross the barrier. if they increase the temperature, this then tends to 1, right? Meaning that all the particles have enough energy. But also these curves, depend on voltage, right? So how large is this potential difference? So if you increase the potential difference, fewer and fewer of these particles have sufficient energy, okay? And essentially, this is now it, right? So we want this equilibrium condition, right? Where the flux out to in and in to out is the same. These are our two expressions that we're gonna use. Conveniently, the gamma, which contains all of this information that we don't know, we're gonna assume it to be the same in these two fluxes. And so you can now equate these two and derive the equation for the equilibrium potential, okay? And I guess we're gonna stop here. I'm gonna, I guess, answer some questions, and then we're gonna take a short break and come back in 10 minutes. I mean, the lecture is gonna start again in 10 minutes, or maybe I'm gonna answer about 5 minutes of questions if there are questions, and then.
So there are 2 questions right now that we can probably answer. So Adrian asked, like, if having a fever lowers the membrane potential slightly. Because I'm talking about the temperature, how it affects the membrane.
So I guess the temperature will affect these equilibrium potentials. I guess this would be the case if well, so temperature actually has the opposite effect, I guess, right? So if temperature increases, the equilibrium potential actually increases, right? Because you have more particles have more energy, so you will be able to sustain a larger potential difference, right, at equilibrium. So it's the opposite effect, I guess, of what you said. If you only have one ion type, in reality, the resting potential, it's dominated by potassium, but it also has other particles that contribute to it. So one would have to see, and temperature may have opposite effects on their potentials, but one would have to think this through. Yeah, I'll give you an equation later on that describes the contribution of many ion types.
And now another one that was before, asking about, so the channel itself is not direction selective?
That's what we will assume, yes. We will assume that it's not direction selective, and that the only directional effect is given by this asymmetry, right? That when you go one way, you have to cross an energy barrier, and when you go the other way, you actually just get sucked down this energy landscape, right? So this is the source of the asymmetry that we're going to assume, and as I said, these gammas, we're going to assume that they're the same. And this is not, I mean, we're making a number of assumptions, but this equation actually turns out to be a pretty good equation in practice to describe the potentials and the effect of these factors on these equilibrium potentials.
Yeah.
Valeria, shall we just do the break right now? And then
so let's take a break, and then we'll be back.
Collect the questions and we just
yeah. So again, because we were a bit late, we'll have a short break. We'll be back at in 6 minutes, pretty much.
Okay.
Okay. Are we stopping the record? You're recording. Call is recording. Okay. Good.
Right. In our thought experiment, this would be true. Right. So if this was in a vacuum, then you would actually feel there would be an electric field, right? There would be a potential difference also pulling you towards the cell. But this is not a vacuum, right? This is in a conductor, which is, water filled with ions. And so inside of a conductor, you don't have an electric field, right? So charge moves around such that all the excess charge essentially lies here on the edges of the membrane. And the only electric field, which are these arrows, is the one that goes across the membrane, right? So there is no electric field outside or inside. So the process of getting to the entrance of the channel, in the first approximation, is only driven by diffusion, right? You're not feeling any attraction from the cell. And that's why this term only appears in the inside to outside, right? Because it doesn't affect whether you're going to make it to the entrance of the channel. That's all captured by these first terms, right? That just depends on, you know, how hard it is in general to get there, how many channels there even are, and how many particles you have. So that determines how likely you are to get to the entrance of the channel. And then the energy only starts playing a role when you get to the entrance to the channel, because that's where the electric field exists. And then, you know, whether you have the kinetic energy that you have determines whether you can make it from one side to the other, but only in one direction, right? In the other direction, you will start being pulled to the other side, so you don't actually need any energy. Right, there was another question about whether that essentially this is kind of a circular argument that we're making, that you have concentration gradients that create the voltage and the voltage that creates the concentration gradients. And I guess this maybe I didn't explain enough. The concentration gradients are due not to the voltage, they're due to the pumps, okay? The pumps are these molecules that continuously move stuff, you know, ions between the inside and the outside, and they create these concentration gradients, okay? The voltage is generated in the end because these concentration gradients exist, so that's correct. But it turns out, and I have a slide that you can go through, that only a tiny, tiny fraction of the ions that are inside actually have to move to the outside to establish this, this concentration difference, right? So, you know, we essentially here, we're making an assumption in the end that these concentrations are not changing, right? So that we have this concentration inside, this concentration outside, and that in fact, these small fluxes that are creating these membrane potentials are actually not affecting the concentration. So that these are fixed, right? That these do not change. And that's actually a good assumption in many cases, because the number of ions that you need to move before the equilibrium reached is tiny compared to the number of ions that you have overall, okay? So really the concentration gradients are created by the pumps, and the concentration pretty much doesn't change. You can think of it, at least in this derivation, as not changing, right? Because the number of ions that move to create this potential is really, really small, okay? And then there was a question that I didn't quite understand that went back to the thought experiment, where essentially we have positive and negative charges. And there was something about, you know, the only negative charge that we considered that was enriched outside compared to inside was chloride. And is this chloride sufficient to create the negative potential? So that's actually the wrong way to think about it, right? So what we just did here is I showed you, you don't actually need a negatively charged ion to create a negative potential inside, right? You can have a positively charged ion that is enriched inside that will want to leave. And as it leaves behind negative charge, and that creates a negative potential inside, right? So this brings me back to this, right? So this equation is what we derived for specifically for potassium, right? Now you should really go through the exercise and trying to think about how this would play out if you had, say, a larger concentration of potassium outside compared to inside, or if you have a negatively charged ion that, again, can either be enriched outside or can be enriched inside, right? You have these 4 cases, and if you go through them, you will find that you always get variations of this equation, and the general equation is this one, where essentially you have the Z term, which is the ionic charge, right? So for chloride, this will be -1, for potassium, it's +1, for calcium, it will be +2, okay? And you know, this has a sign, right? So if you change the sign of the ion, you change the sign of the equilibrium potential. And also if you change the concentration outside to inside, I mean, this is over here, but we can go through these, right? So first of all, in this equation, right, as I mentioned, we have no dependency on this gamma term, right? So this gamma, for example, captures what is the actual conductance through these channels, right? Do you have 100 channels or do you have 1,000,000 channels? It actually doesn't matter for this derivation. And that's because we're looking at the steady state. You know, we have waited essentially until infinity, time infinity, until the equilibrium was reached. Once you start looking at processes that are not at equilibrium, right? When you actually open one of these channels and one type of channel, then close them, for example, as it happens at synapses, or as it happens during the action potential, then certainly the term that describes the conductance will come into the equation, right? Because the more conductance you have, the faster you can move charge and the faster voltage can change. You have this effect, the one about fever, right? So if temperature increases, then the absolute value of this V equilibrium increases, right? But this can be an increase or a decrease depending on the sign of the voltage. Again, if you increase the reason this happens, right, is because, as I mentioned, when the temperature increases, you have more thermal energy. So you have more particles that can make it across a larger potential difference. And that's why you can sustain a larger potential difference. Instead, when the charge increases, this potential, the absolute value of it decreases. And that's why, because if you have twice the charge, you need twice the energy to cross the energy barrier, right? So you will have comparatively less ions that can do that. If you change the sign, of Z, you change the sign of V, as I said, and the dependency on concentration is this one, right? Essentially what happens is that the sign of this term flips when you go from the concentration outside being larger than inside to the concentration being larger inside than outside, okay? So you can spend some time thinking about this and just making sure that this makes sense. And there was actually another question that I want to mention, something about hydration and how these ions are actually embedded in a lot of water molecules and so on, and isn't there energy that is unaccounted for when we need to break these bonds? And so this is actually, this derivation of the Nernst equation is not the real derivation of the Nernst equation, right? So there is a derivation that is based on a much finer understanding of the actual microscopic processes, the actual diffusion processes and so that are happening, that takes into account more of these effects than what we have considered here. But the point of this derivation was just to show that actually it kind of makes sense, right? With some fairly basic arguments, one can come up with somehow which various factors, which various parameters must affect the equilibrium potential, and what the direction of their effect might be. So yeah, this is not the most rigorous derivation of this equation, but there are other derivations that you can look at that take into account more effects, and they end up with the same result. Okay, and now, so what does this mean? If we consider one ion type at the time, right? If there was only one of these that was enriched, and so these are actually these concentration differences. This will depend on the animal that we're looking at, right? This is for the squid, which is an important animal. This is the animal that was used to develop the model of the action potential. So we'll talk about this in a few lectures. And this is now at 20 degrees, right? So this is an animal that lives in water, right? So the body temperature is the temperature of the water. And sure enough, this will affect these equilibrium potentials. And you can see that now for potassium, as we said, you have a negative equilibrium potential. For sodium, which is also positive, but which is enriched outside compared to inside, you now have a positive equilibrium potential. For chloride, which is enriched outside, you have a negative potential because it's negative. And then for calcium, it's again positive. Okay, so you can just play with these numbers and see that this works out. And we haven't considered yet the case where, in fact, you have more than one channel type, right? That is open. And we'll do that in the rest of the lecture. Let's see how much time we have. Well, I'll go through this quickly. This is important, but you can think about it more on your own. And anyhow, this is really just the back of the envelope calculation, right? Again, you need to take this with a grain of salt. But people, you can come up with a number of what is the membrane capacitance, right? The capacitance is the parameter that tells you how much charge will be stored across the membrane for a given potential difference. And these are the numbers that you get for the specific capacitance. You can kind of estimate what the area is of the membrane. And so you can come up with a value or a range kind of capacitances for the entire neuron. You can also then, using this number, figure out, okay, how much charge do you actually need to have across the membrane to sustain an equilibrium potential of say, minus 70 millivolt. You can, plug in this number here and you get this charge, right, in Coulomb. Then you can figure out how many ions this is. If you have ions that have just one charge, like potassium, and so you have, say, about 10 to the 9 ions that need to move, right, from the inside to the outside to create this potential difference of, say, minus 70 millivolts. But now the question is, how many ions do you have in the first place inside the neuron? And that's where you go back to this slide that I showed you a bit earlier that tells you kind of how many ions you have per unit of volume. Now, you make some assumptions about how big a neuron is, and you get numbers that critically are many orders of magnitude larger than this, right? So with these particular numbers, one neuron contains, say, in the order of 10 to the 14 ions, but the number of ions that actually need to move between the inside and outside to establish this potential are only 10 to the 9, right? So many, many orders of magnitude less. So for every 100,000 neurons, in this case, for these particular numbers, right, that are in the neuron, only one has to move. And so this assumption, actually, that the concentrations are fixed, they're actually not changing by opening these channels, in this setting is actually appropriate. We'll consider another setting in a few slides where this is not the case anymore. But in the basic derivation of this equilibrium potential, for one ion type, again, you need very few ions to establish these potentials. And so the concentrations, you can think of them as being fixed. Right. This obviously gets worse if you consider smaller and smaller segments, right? For example, if you now make this calculation, say, for a synapse, which is a much smaller volume, then, because the capacitance goes with R square and the volume goes with R cube, things get worse and worse. So this ratio gets smaller and smaller. So there's a question.
Yeah, so there's a question about the A value. Is the total area of the neuron axon surface, and does it make more sense to measure capacitance per length unit here?
So this, I think, this will be, we're assuming more or less a neuron that is a sphere, okay, just a soma. It's an approximation. Again, it's a back of the envelope calculation, okay? The basic idea is that what is comforting is that you really have orders of magnitude. But yes, as I point out, this only is true for, large enough volumes, right? But again, we will see that most of the time, actually, when neurons are doing what they do, they won't be at equilibrium. And so this actually will mean that the flux won't be, the total flux won't be zero. So that's why you have pumps, right, that continuously maintain these concentration gradients, even though in many settings you do have eventually a net current flowing for a particular ion type, but the pumps, just revert back the concentration gradients continuously. Okay, and actually that's what we're going to discuss now. So all of this derivation was about finding this equilibrium potential, right? So we say, okay, we know there is an equilibrium, we know that there is this concentration gradients, we know that there are these selective channels, so what is the equilibrium potential? But now what happens if, due to some external influences, for example, current coming down the dendrite because the synapse opened somewhere, what if this potential is actually not at equilibrium? And again, we can get the basic idea of what must happen by considering this potential difference and these two fluxes, right? So this is the equilibrium setting. It's a dynamic setting, right? Microscopically, you have some flux of ions that go from from out to in, some from in to out, but on average, these are the same. So the net flux, the sum of these two, is 0 at equilibrium. Now again, we're going to do this for the example of just potassium, okay? And now what happens if the potential is actually inside is smaller than the equilibrium potential? Now, for the reason that we discussed before, right, because this potential doesn't actually appear in the equation of the out to in flux, right, this actually stays the same compared to before. But because there is now a larger potential difference, you have proportionally less ions that have sufficient energy to cross this potential barrier, right? And so overall, the flux from in to out is smaller. And so now you have a net flux of potassium that goes from the, I mean, this is flowing in. So you have net potassium flowing from the outside to the inside. And because now you're taking positive charge and bringing it inside, you are increasing the potential, right? So you're essentially pushing the potential back up, okay, towards the equilibrium. Now, if you take the opposite case where the voltage potential is larger than the equilibrium, again, this part of the flux out to in is unaffected. In to out is now larger because now the potential difference sorry, this one is smaller. So you have proportionally more ions that can cross. So now you have a net current of potassium that goes out. So you're taking positive charge with you, you're leaving back negative charge. So you are reducing the potential inside. So you're going back to equilibrium, right? This is just a different way to say that this really is an equilibrium potential that is stable, right? So if you perturb it away, you will come back. And the easiest relationship, that could exist, if you now look at these currents, right, of potassium through the membrane as a function of potential, would be essentially a line, right? And this line, right, is described by this equation. So okay, let me first say this, right? So this is what I just said before. If the potential is positive, right, then you have a current, potassium current from that is going from inside to outside, right? So that would be, say, this positive value. If the potential is smaller, so the case we had down here, you have a current that has the opposite sign. And both of these currents have the property that they tend to push you back towards the equilibrium potential, right? Again, and so now if we say that we have, so that's one reason why actually these equilibrium potentials in the end, they're called reversal potentials, okay? And they're called reversal potentials because at this voltage, at this V equilibrium, the current, the sign of the current through these channels, carried by this particular ion type, reverses in sign, okay? That's why it's called reversal potential. So we're gonna call, say, the reversal potential for potassium, which is this equilibrium potential that you would obtain if you only had potassium, which you can derive with the Nernst equation. We're gonna call this EK. And so then this linear relationship, which you are now, again, it's kind of an assumption, but it's an assumption that turns out to, be pretty good in many cases, that for many channels, they actually follow Ohm's law, right? This is a basic law that describes current through a resistor or a conductor. So the current is the 1/R, right? So this is the conductance G times the potential. And here the potential is V minus the reversal potential, right? So that's just the equation that describes this line. And so this is a very simple relationship, but now it allows us actually to still understand a bunch of other stuff about what neurons can do, okay? And for example, we can ask, okay, what happens now if we don't have one ion type, but instead we have two ion types, okay? So now we're gonna assume, okay, we're gonna consider both potassium and sodium, right? Each of them are associated with their own channels, right? They're private channels that they can only go through. And now we're gonna let these two processes run, right? And we now just derived an equation we assumed really an equation that would describe the current through each of these kinds of channels, if the potential is different from the reversal potential, right, which is the corresponding equilibrium potential. And so, we have talked a lot about potassium, right? The reversal potential is about -70, and I showed you before, sodium has a reversal potential that is positive, right? That's because it's also positive charge, but the concentration is larger outside than inside, so that flips the sign of the equilibrium potential. And so we can now draw these curves that describe, this one is the current through the sodium channels. This is the current through the potassium channels. And now, will there be, what happens if both of them are open, right? And what will happen is that a new kind of equilibrium will be reached, which is essentially the potential here for which the current through the potassium channels is exactly opposite the current through the sodium channels, which is the case at this particular value of the potential, right? So this is IK, the current through potassium, INA, the current through sodium. They go in opposite directions, and so they cancel out. And so at this potential, again, things won't change, even though now you have a net current flowing both through the potassium channels and one net current flowing through the sodium channels, but the two cancel out together. That was a question?
Yeah.
Is the resting potential of neurons universal, or are there more than one resting potential?
So I can barely hear you.
If there is the resting potential of neurons, it's universal, or there is more than one resting potential?
Okay, so now we're, I guess, defining a particular term with this, which is the resting potential, right? So for now, we have been kind of using these as synonyms, right? So the resting potential is the potential at which the neuron usually sits, okay? And so what is the resting potential? So this is now jumping a bit ahead. The resting potential essentially is the reversal potential of a particular type of ions, right? And it's actually an ion type, which is, a channel type that is permissive to more than one ion, but it's dominated by potassium. So the reversal potential of the neuron, the resting potential of the neuron is very close to the reversal potential of potassium, okay? But you have now, so there's many different kinds of channels. The channels that are always open, right? These are just, they have no dynamics. They're just there in the membrane. They're always open. Those are the ones that determine the resting potential. But now there are other channels that can also open at different times, because there was neurotransmitter released at a synapse or because of other effects. They have their own resting potentials, and essentially what happens is that they will now affect the actual potential of the neuron. But this particular potential here won't be the resting potential. It will be a different potential. So I hope that answers the question. But we're going to actually, talk about this more, right? So the basic idea now, again, is that you have kind of a new equilibrium. There's now a big difference, right, with the equilibrium that we were considering before. Before we were considering these equilibriums that exist, that arise when you only have one channel type. And when you only have one channel type, we reach the situation where the flux between inside and outside for that channel, for that ion type, for the corresponding ion type is zero, right? So you have no changes of concentration anymore over time. But in this particular equilibrium, which is given by essentially the combined effect of these two channel types, now you do actually have net currents of both. Okay, so here is a misspelling, right? So this should say IK and INA. Both of them are different than zero. So now suddenly you are in a setting where there is a continuous flux of potassium, and there is a continuous net flux of sodium. So this will start changing your concentrations. And that's, again, why you need pumps, because whenever you're not at rest, right, there will be net current, and so the concentrations will start to change, and you need to compensate for that with the pumps. And now what happens?
There is just one question on the previous slide saying why in the previous one. I guess, yeah, exactly. Why V it's greater than V equilibrium, and why this leads to increase and flux into the out?
Because if you remember, the flux from in to out is limited by the fact that not all ions have sufficient energy to cross this energy barrier, right? So that's this Boltzmann factor that tells you what fraction of the ions that make it to the entrance of the channel will have sufficient energy to cross this energy barrier. And in this particular case, for the blue line, this energy barrier is smaller, which means that you have a larger fraction of ions that can manage to cross. And that's why the flux is going to be larger compared to, you know, the situation that we have here at equilibrium, okay? Okay, and now, you know, we can start playing games. And so what happens if we now increase the conductance of one of these channel types? And increasing the conductance essentially means opening channels, right? So some of these channels, neurons can open or close them, again, based on effects like of neurotransmitters and things like that. So what happens if you now increase the conductance of one of these channel types a lot? So for example, if you increase the conductance of these sodium channels, what happens is that this slope gets steeper. And so the equilibrium potential that will be reached in this situation, right, where you have these channels open and these channels will be shifted towards the reversal potential, this E and A, okay? So that's what this is saying. And if we now instead lower the conductance, so if we start closing these channels, right, then the slope becomes smaller. And now where is the new equilibrium potential? Well, it's closer to the reversal potential of potassium in this case, okay? So a lot of the computations now that will happen in neurons are essentially based on this process, right? You have a particular channel type that is associated with a particular reversal potential. And now when you open these channels and you open them a lot so that they dominate over the conductances of other channels, then you're essentially pulling the potential towards the reversal potential of that channel, okay? So in this setting where the conductance of these K channels is larger, you're pulling the potential towards this, to this reversal potential. And in the situation before, where this conductance was larger, we're pulling it towards that reversal potential. Yes, another question.
Valerio, in the slides you have like the conductance of sodium being greater than conductance of sodium. Okay,
that's a mistake. So this would be, I apologize. This, I usually give this lecture on the blackboard. So these are new slides, and thanks for any comments and mistakes that you find. So we'll have to correct it. Yeah, so this obviously should be GNA smaller than GK and GNA larger than GK, okay?
And there is another question about, is the conductance independent of the electric field and just dependent on the channel's opening, or?
Yes, that's the assumption we're gonna make, yeah. Though, I mean, it depends. So there are channels we're actually voltage dependent, right? So there will be channels there whose conductance depends on the potential. And these will be the channels that are responsible for the action potential, which essentially will be a positive feedback, right? So you change the potential a little bit, now you open channels more that make the potential change even more, and so the potential changes even more, and the channels keep on opening. So you will, through these effects where the conductance depends on the voltage, you can start having positive feedbacks and create, very non-linear effects like the action potential. We'll discuss this in detail. But, this is not, this voltage dependent is not true for all channels, right? Many channels are not voltage dependent. And in fact, some channels, like the channels that really determine the resting potential of the neurons, are pretty much open all the time, right? There is nothing that changes their conductance. Okay, now, you know, as I mentioned, in reality, so we have considered the situation where we have derived these reversal potentials, right, for the case where you have one ion type. You know, this is the Nernst equation. And you can already imagine now, based on this reasoning, right, that if you have more than one channel, or sorry, more than one ion type that are associated with different reversal potentials, you know, if you put them together, you will get something that has a different equilibrium potential, right? This is what we showed here. And so you can actually derive an equation that takes this into account, which is very similar to the Nernst equation, but now describes the equilibrium potential or the reversal potential for a channel that is not just selective for one ion type, but is selective for more than one ion type, okay? And this would be the general equation for channels that are selective to potassium, sodium, and chloride. And they have, you know, again, they're very similar to the Nernst equation, but now you have these terms, P, which is the permeability, which again is very close to the conductance. It's related to the diffusion constant, right, across these channels for these different particles. And, you know, if you imagine that now you have a channel that has the high permeability, right, that is mostly actually selective for potassium, but has low permeability for these other ion types, then this term will dominate. And so you get back the Nernst equation. And the other thing that you can notice in this equation is that for chloride, right, you have this concentration inside in the numerator and outside in the denominator, right? That's because this Z term that we had here that would change the sign of the V equilibrium was now essentially incorporated into you know, the inside the logarithm. Okay, so this is the general equation to calculate the equilibrium potential or the reversal potential for one particular channel type, okay? If that, and this also works in the case where the channel is selective not just for one ion type, but for many ion types. And again, it's, you know, very similar to the Nernst equation. But now, this is really, you know, this already now really gets you very far in understanding how potentials are modified in neurons, right? So what we have now is we'll have one kind of channel, which we have mentioned a few times, which is always open, right? This channel type, this type of channels is in the membrane, it's always there, it's always open, and it has a resting potential, a reversal potential, which is in around -60, -70 millivolts, and that will be the resting potential of the neuron, right? When nothing happens, when no other channels open, where no synapses are active, where no action potential is generated, the only channels that are open are these type of channels, which we can call them leak channels actually, or we'll call them leak channels later. And these are the ones whose reversal potential, which you can compute with this equation, determines or is equivalent to the resting potential of the neuron. Okay, and you know, these channels, they are again dominated by potassium. They're mostly selective for potassium. That's why the resting potential of the neuron is close to the reversal potential for potassium. But now we have other channel types that are often selective for more than ion type that are associated with their own reversal potentials, which again you can compute with this equation, which is, by the way, the Goldman-Hodgson-Katz equation. And channels that have a reversal potential that is positive, you know, that that depolarizes the neuron, those we'll call excitatory, right? And when they open, and when they open a lot, they will pull the potential of the neuron towards these positive reversal potentials. And say at inhibitory synapses instead, you can have, you will have other types of channels that open, which are associated with a reversal potential that is, say, smaller than the resting potential. And so when they open, they will pull the potential towards that negative reversal potential, okay? And so we will, refine this idea. We'll build on this idea in the next few lectures, but this is the basics. And so then, again, to go back kind of to the beginning about why should one care about these mechanisms, and I just want to say that, again, these resting potentials are the basis of everything, right? So this is how neurons compute. It's also how a lot of other cells do what they are supposed to do. So muscle cells, for example, also work because they have this resting potential. So it's a very important process to understand. And it's also, again, a process that neurons in particular invest a lot of energy in, okay? So you can see here the total energy consumption of neurons, and about half of it, or the brain, I should say, because it also includes glial cells, and about half of it is dedicated essentially to these potential, right? So, and a big part of it is actually just maintaining the resting potential. And then you have, the energy that is related to recreating the concentration gradients after an action potential and things like that. Okay, so a big part of the energy goes into creating these resting potentials, and that's one reason that the brain consumes so much energy in relation to its mass. And this really also has consequences, right, for computation, or at least it's a way to see that it has been taken advantage for measuring computation. So because neurons consume so much energy, in particular when they are active, right, when you start depleting concentrations and you need to use your pumps, right, that is one process that requires a lot of energy. And so the brain has developed very efficient ways to shuttle energy, right? Oxygen and so on, and to parts of the brain that are really requiring it for computation, right? And that's the basis for example, functional magnetic resonance imaging, right? Where I'm sure you have all seen some of these maps where you can see parts of the brain that are active. And this is not a direct measure of brain activity. This is an indirect measure, which is essentially telling you where oxygenated blood is being sent to sustain these processes that require a lot of energy. Right, and to finish on a light note, right, this also made it into popular culture. So I'm not sure how many of you still know this movie, which is now quite old, but the whole premise of it was that humans are essentially batteries and can be used for energy production. And I'm not sure exactly about the premise or the movie itself, but certainly the idea that cells are batteries, that's actually pretty correct. Okay, so we'll stop there. We have a few minutes for questions, and then when we're done with questions, again, we have this this introduction of ETH juniors, and I'm not sure if the person that will do this is actually here. This would be a few minutes after the end of the lecture and before the exercises start. So thanks everybody, and yes, for those who will leave, I'll see you at the next lecture, I guess. But so do we have any questions?
Not so far. Thank you, Valerio.
Thank you.
I'm looking at the chat.
So shall we do the introduction then?
Yes, I don't see any questions. So yeah. Marcel, are you here?
Yes, thank you,
okay.
Professor. we can't share our screen yet. If you could allow us to do that, so we could show some slides.
Okay. Let's see.
Now it should be working.
Yes, it works. Yeah.
Okay, so thank you very much that we can use your time to present ETH Juniors. I'm Leah, I'm studying mechanical engineering.
I'm Marcel, and I'm also studying mechanical engineering.
Yeah, so, so what do? We are, as ETH Juniors, we are a student enterprise, which has the goal to connect the industry with you as students. So we acquire projects from big companies like Alfa Romeo or Novartis and give you the possibility to work on these projects and gain some hands-on working experience, work on exciting problems. And this with flexible working hours. So if you have time to work 100%, you can work 100% or just 20%. And compared to other student jobs, it's also a really competitive salary.
To show you what we've done in the past, we brought you 3 example projects that we did just recently. One of the projects was with Rega. We helped them design and build a prototype drone that was able to use, or with the help of computer vision, to detect people in help. With Alfa Romeo Racing, I'm sure you know the Formula 1 team. We helped them to design and build a pit stop rig, which was a simulator where the mechanics of Alfa Romeo were able to practice the tire changing process and through that improve their time, through which Alfa Romeo is now, I think, at the moment, the 2nd fastest team in the pit stop tire exchange process. We do not only do IT and engineering projects, but also do process analysis, for example. We did an interesting project with Swiss, where we helped them analyze their in-flight catering system all over the world, and through that help them improve their flight times and their efficiency with the catering process. If those projects sounded interesting to you, pull out your phones and scan the QR code and sign up under our platform, or visit signup.ethjuniors.ch. And once we have a new project that will fit your profile, we'll hit you up and you'll be able to work with ETH Juniors on such a cool project. If you have any questions, feel free to reach out to us with the email below. And just letting you know, if you sign up during the next month, you have the chance to win one of 20 Digitech Galaxus vouchers in the value of 25 Swiss francs. Thank you very much for your time. Thank you, Professor, for giving us a chance to introduce us. And I hope we'll see some of you signing up for the platform. Thank you very much.
Thank you.
Great, thanks. So I guess we will have a break. I don't see any questions. And then at 10:15, the exercises will start. Thanks, everybody.
Yeah, exactly. See you then later in 15 minutes.
We just go out and start. We're gonna hear it.
Unmute.
Okay. Are the mathematical relationships to you? Okay. Welcome everyone to the exercise session. Yeah, so basically what I'm gonna do is, so we have the solutions, so we have a PDF with the solutions that will be uploaded at the end of this. You cannot hear me, why? I'm
They
muted.
can.
Okay, okay, good. Okay, good now, they can. Okay. Adrian, can you hear me now? Okay, good. Okay, so welcome everyone to the exercise session. So basically, as I was saying, so the solutions are going to be uploaded at the end of the lecture. So it's just like a PDF that you can go through it. So the idea of the exercise session is that I mainly respond like more specific questions. Of course, you can always contact me, but it's just easier to have this time that we can just solve more more questions if you didn't understand a question or whatever. Yeah, so let me, so there's no time that you have to upload your responses. You don't have to. This doesn't count for us. Like this doesn't count for the grade, so it doesn't matter. You don't have to. It's just for you and also for us to know where do people have problems, like in specific questions, in specific topics, so it's easier for us. So we normally try to respond and give some feedback, but of course you're a lot of students and we're only 3 TAs, so sometimes we don't have the time. So what we usually do when we have a lot of solutions uploaded, we just go through them quickly and then check where, like, okay, well, people didn't have problems like finding I don't know, a specific solution. So we just try to focus on the rest. Okay, so I'm gonna share. Yeah, let's just go quickly through it, and yeah, you can just write in the chat or raise your hand if you have any question. Okay. Okay. So. So the first exercise is this one. So this image, which is basically explaining how do we translate some stimulus into some electrical signals, and then how the brain is basically interpreting this this input. So well, in general, you all know, right? Like the brain, as we saw in the previous lecture, that we need almost nothing to interact with the world, right? So the basic of the brain is just, you have some input, and then we just have some networks that responds to this, that will respond to the environment. And now the question is just the simplest question, right? How do we react to the environment? How do we perceive the environment? So in this case, this is an example of some just some mechanoreceptors, so some just like pressure, or how do you feel something in your skin, but you can imagine of different stimulus that can come to your to our brain. So for example, how you see is because you have some receptors in your retina that respond to light intensities. How do you perceive heat? Well, there's also like some receptors that can perceive the temperature, and so your skin perceive like changes in pressure, and this is just like different ways to have this. Also, for example, to smell or taste is just some chemicals that actually bind to receptors, and that's how you can you check the question? You can check the chat. Okay. So that's how we just perceive the environment, right? So the first question is, okay, so in this figure here, that we have this neuron under stimulation. So okay, for this particular neuron, the stimulus is a stretch of the muscle it is attached to. And then what could be the use of having a stretch receptors in our muscles? So basically, you can imagine that sometimes you need this stability, right? So in this case, we have, if I do quickly, if I go like this, can you see?
Yes.
Okay. Okay. yeah, so basically it's just somehow to have like some stability in our yeah, just to respond to this. So imagine like if is the reflex, right? So you have if you're walking and then somehow there's some way to like like just make your muscle a bit unbalanced, your body tries to react and compensate for this. So the reflex are good for that because it's trying to quickly respond to some changes, some rapid changes that are not used for the muscle. And in this case, and actually it's just, this is a bit, yeah, okay. So that's how we have these like this kind of stretch responses. What other types of stimuli can you think of? Other types of sensory neurons is what I just said, that we have just some like light intensity, temperature, pressure, chemicals, and so on. Okay, what happens to the receptor potential if you double the amplitude of the stimulus? So yeah, some of the questions that we saw, you respond correctly. So the more you stimulate the neuron, the more this will be in the membrane potential of the neuron, of the receptor. So what happens if to the receptor potential if you double its duration again? So the more you stimulate a receptor, the more it will respond. And so these just questions are just to basically respond the next one, which is like, is the receptor potential an analog or a digital signal? So it's analog, is graded. So it's basically the more you stimulate this receptor, the more you will respond, right? It's not all or none. It's not like I stimulate and then I create an action potential, or I don't. Then we have the summing or integrating this part. So it says, okay, so how is the signal transformed? How is the information about the stimulus, the amplitude encoded in the axon? Wait a second, let me just, I cannot see where to. Gonna go back to this. Okay, sorry. Ooh. Yeah, sorry. Okay. Yeah, where was it? Okay. How is the signal transformed? How's the information about the stimulus encoded in the axon? So, okay, so basically the neuron is integrating this potential, and then at some point it will start spiking, and this happens when you reach the threshold. So today we saw this. We saw that where's the resting potential of the neuron. So basically is where no action potential is generated. But once this threshold is reached, the neuron will start responding. Okay, and then what would happen if we reduce the amplitude of the stimulus and then just a number to 1/10 of the original strength? So if we don't stimulate, if the neuron doesn't get enough stimulation or enough membrane potential, like the membrane potential doesn't get above the threshold, then basically we could just not generate a spike. Okay, so then now we go to one of the questions that I think a lot of people were having troubles with. So it says that it asks you to sketch the firing frequency, so the number of spikes in an interval of time as a function of the stimulus amplitude. And then they ask us if the line we drew intersects in the origin or not, and why or why not. So what they're asking us, basically here. So yeah, okay, so it was a bit confusing maybe. So when we said the stimulus amplitude, because I saw some responses of like, oh, the amplitude, like the member potential. No, we're not talking about the member potential of the neuron. We're talking about the strength of the stimulus, right? So it could be arbitrary units, like how the intensity of the light, or it could be, I don't know, like Celsius, the temperature. So this is just like how like the strength of the stimulus that we are applying to the neuron. And then in the y-axis is how, like, what is the spiking frequency of that neuron, right? So in here we have like few spikes, then we have more spikes, and then basically we have like a burst of spikes. So this will be like the firing rate. So as you can see, it's just as the more we stimulate the neuron, the more spikes you will have. And then basically we get some curve like this. A lot of people, like some people draw it like this correctly and just linear. Yeah, I mean, the reasoning behind it, it's correct, but in reality, we do have some saturation. And why is that? Because we don't have infinite resources in the neuron, right? So basically, like the neuron starts spiking, and then we have some neurotransmitters, and then it just keeps spiking. But at some point, these resources have to be generated again, right? Like in order to have the neurotransmitters, they have to go some transportation to the axon, to the soma, and then bring them back. So that's why we have some saturation. So at some point, no matter how much you stimulate the neuron, it's just gonna saturate the response. We have some questions in the chat. Can you check them? Mm-hmm. And so yeah, that's the part here. Now, what about the part where does it intersect in the origin or not? So and this we find a lot of I don't know, it's debatable. People really get confused whether like they drew this plot and they say it does not, it intersects with the origin. What we mean is like, yes, of course you start here. So this will be the origin, like zero stimulus, zero spiking frequency, and like, or it will be like, do we intersect in the origin of the, do we have a spiking frequency from the beginning? Does this is like shifted this way? And it's not. And the idea is that we understand that at the beginning there's going to be a stimulus and there's not going to be spikes because we haven't reached the threshold. So it's up to a point that we have some certain amount of stimulus that the receptor is able to surpass the threshold of the neuron, and then the neuron starts spiking.
So there's a question asking, does the spike frequency start from zero, not from the origin, from the threshold value?
Does the one?
The spiking frequency starts from zero, not from the origin, from the threshold value.
Okay, yeah, but just because, yeah, so that's I don't know if I understood correctly, but maybe just because you think this axis is the membrane potential of the neuron. It's not. This is not that here starts the threshold of the neuron. This is just the strength of the stimulus. So there's no membrane potential in this plot. It's just how the neuron responds with respect to the stimulus. So let's say in this part here, at the very beginning, you just have this in the neuron. So you just have, like, if you have to, at the very beginning, you have this much stimulus, right? You stimulate the receptor, you stimulate the neuron, and then so that will be like, I don't know, in arbitrary units, like this much pressure. Okay, and what is the firing rate of my neuron in that point? Well, 0. You see, there's no spikes here because you didn't generate anything, because you didn't get any spikes. And then you put a little bit more, and then nothing, because the neuron is still not able to reach a spike. And then until at some point is when the stimulus is it's large enough to start generating spikes, and that's when you count this frequency.
Second question, doesn't the amplitude of the stimulus first gets converted into the receptor potential, and this has to reach the threshold to produce an action potential? So it's like the amplitude of the stimulus gotta be converted into the receptor potential, and then this is gonna generate the action potential. Is that the case?
Yeah, so basically here, it's a bit confusing with the amplitude of the stimulus. So yeah, the stimulus is, as I said, it's in different units, and then different receptors have their own way to transform this into a potential, right? So how do I say it, like with an example? Yeah, okay. So for example, in the cochlea, and then maybe you will see it in your classes later. So the way that it works, or the way I like this example, how you listen. So basically, there's some vibration, some pressure in our I mean, basically noise is just pressure, and then these waves are transformed into a mechanical. It gets transformed into a mechanical stimulus by moving some water liquid that is inside our cochlea, and then it starts moving it back and forth. And this movement makes these small cells that you will have in the cochlea and hair cells that just moves back and forth, and these back and forth open the channels, and that's when ions start flowing. So for different receptors, you have a different way to, it's not exactly the stimulus itself, it's how do you call it? It's just the different receptors will have a different way to transform this strength of the stimulus into a membrane potential. So this basically, look at it like the strength of the stimulus will create some change, and this depends on the receptor, into the receptor potential, and then the receptor potential is what we have, like ions flowing, and then this is increasing the membrane potential of the receptor. And if we reach the threshold of the neuron, then the neuron will spike. I don't know if that makes sense. Okay. That was the only thing.
Yeah, I'm checking.
Okay.
There's another one. Would a neuron not also fire spontaneous action potential? So there would be a very low firing frequency at stimulus amplitude 0. Doesn't neuron just fire because of nothing?
No, well, okay, so it depends on the neurons, right? So there's neurons in, there's a lot of noise happening all in our cortex. Here we're looking at some stimulus happening at the periphery. And I mean, of course there can be background noise, but in this case, some neurons are really specific to respond, right? So if think of it like every part of your nervous system wants to convey a specific message. So in this case, this neuron, it specifically wants to just give information about certain pressure in your skin, right? So this, I will say, this neuron is not gonna be activated unless you really touch its receptor field and you really like stimulate the neuron.
Is the spike frequency stimulus amplitude curve related to Weber's law? I don't know what's Weber's law. So
no, we can check. I will check that and then we'll respond.
Okay, just as the question.
Okay. Okay. Yeah. So yeah, that was one of the question that we have a lot of like problems with, which is like just to draw this sketch of the spiking frequency of the neuron with respect to the amplitude of the stimulus. Then we have yeah, okay, so then we see that, right? Once we reach the threshold, we have spikes, and then the question is if the action potential is a graded or an all or none mechanism. So it's all or none. So either the neuron spikes and conveys the message, or it doesn't, right? And this is it's just basically to make to make sure, as in the terms of computation, to understand how things are happening in the brain, right? So you have some analog signals which are more like specific or like more sensitive, and it's a way to convey the message, but somehow we also need some fast way to convey another message, and that's the all or none. So in terms of computation, that's what it's important to be understood, right? So it's a graded signal, and we have a combination between analog signal and then an all or none mechanism, so a digital signal. How does the amount of neurotransmitters released depends on the number of spikes. So here again, we're gonna see, so we see how do we respond in the membrane potential of the neuron, how is this response, how this response is when we look at the action potential, and then we talk about the neurotransmitters that are released. So here in this example, we can see it. So when the neuron starts like spiking, so this will be the presynaptic neuron, it will start like sending action potentials to the next neuron, right? Sorry, it will start stimulating the next neuron. And this will be by just basically outputting neurotransmitters, and these neurotransmitters will have a cascade, and then the idea is to get the other neuron to spike and so on. So if you have few spikes, then the neuron will only release few neurotransmitters, and then the more spikes you have, the more neurotransmitters will be released. And as I say, for example, here with the saturation, at some point you just cannot, there's no way that the neuron can keep generating a lot of neurotransmitters, because there's infinite number of neurotransmitters at a certain time. So then if the question is if this is a computation, if this is analog or digital. So we see it here in other, we will study a little bit more neurotransmitter later, and we can see it also as a digital computation, but here is analog, right? Like the less the spikes, the less neurotransmitters, the more spikes, more neurotransmitters, and then that's like completely different from the action potential. You reach a threshold and you spike, and if you are above the threshold, you keep spiking. It doesn't matter. You don't have like a larger spike, right? You just have a firing rate.
And does it depend on spike amplitude or just purely the rate?
What does it depend on?
So it says like.
Okay. So something like it, the action potential is something that it's always gonna be the same. So it's just an integration, and then you basically have.
They can't see you.
No, yeah, I know. Okay. Trying to draw this. Okay, so let me just show it somewhere here. Okay, so if we zoom in, and then you can see, yeah. If we zoom in into the spikes, basically you will see this, right? So this pattern of like, this will be the spike. So it's integrating the membrane potential and then just spiking. So this is gonna be always the same. So it's not that, oh, because you have more stimulus, then you have a spike like this. That doesn't happen. That's why it's an digital or an all or none. It's like, it doesn't matter. So this will be translated in the firing rate. So yes, the more you stimulate, you will have more spikes, but the spike itself, the action potential, is always the same. It looks exactly the same all the time. So it's just the same amplitude, the same shape, and so on for a specific neuron.
Do all spikes get created in muscle spindle and get transmitted through the axon?
Okay, repeat it.
Do all spikes get created in the muscle spindle and then get transmitted through the axon?
I mean, any spike that will be, yeah, any time that the neuron has spikes, then it just transmits, it just flows through the axon and then tries to transmit this information to the next neuron. Whether the next neuron is activated or not depends on how much stimulus it gets from different neurons. I don't know if that's like,
I think
because
so.
yeah, if I ever do not like respond properly your question, you maybe I didn't get it, just keep posting like, oh no, I meant this or something, because maybe I didn't get it properly. Yeah, what is the other question?
The more you stimulate means the more frequently you do it. We don't care about the amplitude of a stimulus so far. It is higher than a threshold, right? You don't care about this amplitude of a stimulus as long as it's higher than a threshold. Like, it's not like that. So the question, the more you stimulate means the more frequently you do it, but it's not. Like it really depends on the input, the amplitude of the input, right? It's not just the frequency, but this doesn't translate for the amplitude of the spike. So I guess there is a confusion here between the amplitude of the input and the amplitude of the spikes. So we don't care about amplitude of the spikes because they're all the same, but the amplitude of the input matters.
Yeah, exactly. The amplitude of the input matters. Like just amplitude is a bit of like a weird word. Yes. I will say the strength of the stimulus is what matters. So the more stimulus you put into the receptor, the more it will respond, and the most likely that it will generate an action potential. But yeah, I think the problem here with the word is the word amplitude, because then you get confused with the amplitude of the like of the action potential. But it's just yeah, it's just the strength of the stimulus.
Maybe it's easier to ask like in a voice.
Yeah, so this is just related with the neurotransmitter. It's also an analog signal. And then what kind of computation operation, what kind of computation we're having here. So basically it's just that the message here is that we can see that the system is just doing analog to digital to analog conversion, right? So this is how the brain works. The brain has these two different ways to communicate, either with the analog, just the graded signal, or all or none signals. And why does it make sense? Well, because imagine that first of all, we cannot just be communicating everything. Every time you just stimulate your skin, you're just gonna have neurons spiking all the time. It gets super confusing, right? So the idea is that we have these sensitive parts of like, okay, there's some touching, and then there's some integration of the stimulus, and it's like, okay, it's enough for the receptor to say there's something happening. Now I'm gonna start communicating this to the brain because I need an action, right? So it's just a way to have like these different like levels of sensitivity in our brain. There are more questions? No. Okay. Yeah, so let's see. Yeah, so I mean, here I just have some examples. So just an example of like another receptors. So yeah.
What determines the number of spikes generated by a neuron? The frequency of the input is not the amplitude. No, it's not the frequency, it's the strength of the stimulus.
Yeah. Yeah, so the more, what determines the spiking, okay, no, what determines the spiking frequency of the neuron, it's both like the duration, as we see in this example, and the amplitude. So the more you stimulate, the more spikes you will generate in time, and also the longer you stimulate, the more spikes you will generate in the receptor. Yeah, so this is just to show you like, okay, different neurons will respond to different things in different ways. So for the same stimulus, you can have neurons that respond differently. So in this case, for example, there's this thermoreceptor. So this is one receptor that responds to temperature. So the more temperature, it just responds to temperature, sorry. So then here we have the stimulus. So this will be the amplitude of the stimulus. So how much temperature you have, how like the Celsius of this stimulus. And then if you have a little bit of this like change of temperature, it will spike a little bit. You have a little bit more, it will spike a little bit more, and so on and so forth, right? So it's just responding of like, oh, temperatures. So basically look at these receptors like, oh, there's increase in temperature. Oh, by the way, now it's 30. Okay, right now it's 45 degrees. Okay, now it's 50. So this is being translating the number of spikes it's gonna generate. And then if we see another receptor, which will be like nociceptor, which is just, this receptor is in charge of like conveying information about pain. So this one, as you see, is like, okay, 20 degrees. I'm not gonna say anything because it's okay. 30, 40, 45. Okay, well, we're getting into something. And then doing like, yeah, just remove the hand from the pan, man, this is painful, right? So this is just a different way. So how receptors can react to the same stimulus. Yeah, okay, now, so we have now this part in here. Okay, so this is just the stretch reflex. So it says, is the monosynaptic reflex arc that occurs involuntarily when a muscle is stretched. It is also called the knee-jerk reaction. On the left side, you have the circuit of the monosynaptic reflex. And on the right, the activity patterns that involve the neurons when the hammer is tapped onto the knee. So yeah, so this kind of, this is just a small like microcircuit, and yeah, it's really well studied. In general, we always like have it in introductory courses. And then just something that I think it's just nice to see is like how we have these kind of circuits happening at the level of the spinal cord. So, and these are some of the like definitions that we are asked. So we have the central nervous system, that will be basically what is here, like the cortex, the brain, and the spinal cord. And we have the peripheral nervous system, which is basically everything that goes towards all our muscles and everything. So basically through the peripheral nervous system is where we have all these like way to sense the world. And then what here is happening is like, we try to make sense of it. Like, oh, I felt some temperature, but what does this mean? Or this means that maybe I should be more careful when I touch these, because then, so this is all here. But basically our peripheral nervous system is just like all about like, man, there's some heat. Okay, and now we'll just convey this to the brain, and the brain can do whatever you want with it, right? But this is what happened in the periphery. However, not all the computation, or not all the computation. The computation happens in the brain, but not all the reactions will be generated through the brain. So imagine that you need to convey a message super fast, like, I don't know, this retraction like of the heat, or for example, like in this case, the reflex, right? So you hit the knee, and it's not like the brain will travel all this information to your brain, and the stimulus will travel all the way to the brain and say, we were heated, you need to contract, and then it will all the way down. So this is a nice example of microcircuits that happen at the level of the periphery. So then you basically enter into the spinal cord, and it goes really like all the way out, and then like just have some response. And this is why you see this kind of slide. So this will be, if you see at the level of where the receptor is, it goes into the spinal cord. The spinal cord is part of the central nervous system. And then here we have some interneuron, some circuit happening. So what happens here is that you hit the muscle, then the first thing that happens, and this is what you have to feel in this drawing here, is the neuron, the receptor is just gonna send the signal, like there was some stimulus happening here. So the blue ones in this case are the ones that go into the like towards the brain, and then what happened next is like, and then you see here, right? So first, the first one that is going to spike after hitting the muscle is the one that is sensing this stimulus, right? So it's the sensory neuron. And then what is going to happen is like, if you see this connection, is the neuron is connected to this neuron, this red neuron, and the purple neuron. So the next one in reacting is the extensor muscle. So basically, it's just like, as soon as it is like stimulated, this neuron creates like some extensor. So it activates this neuron to be like, okay, so we are heated, you need to extend this muscle, right? So you need, like, let's say, relax it. And then in a way of delay, it will also have this interneuron that it will communicate to the muscle on the other side. It's like, now you need to flex in order to just let the movement happen, right? So this is what happened first. You first have the sensory neuron, and in the schematics, we have this motor neuron that will be the extensor reacting, and then the interneuron, and then finally the motor neuron, which is respond for the flexor.
There is a question.
Oh, yeah.
How do you differentiate a high strength stimulus during a short time and a low strength stimulus during a larger time? We do not in terms of spiking. What matters is, do you get what matters actually when the spike will be generated, right? Can I just stop here or?
No, okay. No, it's just
because the question is like, how do you trans high strength stimulus during a short time and low strength stimulus during a larger time? What's going to happen? Just like, you're going to get more spikes faster because have a large stimulus in a short time, and low stimulus in a larger time, going to get spikes that are like spaced. It's just like the time of integration that's going to change.
Yeah, so I mean, it depends on which kind of stimulus we're talking about. So, and also if we only look at the level of one neuron, right? So one neuron, maybe it's just like doing that. It's just, I mean, I saw it, look at it as in here, right? So in here, it depends on which neuron you're looking at. So in this case, we're looking at the thermoreceptor. So the more temperature, the more it will spike. The longer probably that you keep this temperature, the longer the neuron will keep spiking, right? So yeah, as you said, as Vanessa pointed out, like if you increase the stimulus, you will have an increase in the firing rate, and if you increase the time that you're stimulate, you will just have this firing rate for longer time.
And there's another question. Does the length of the neuron circuit from the skin to central nervous system play a significant role in how long it takes for the signal to travel back if you have to retract your hand or your foot, for instance?
There's a length of what?
Like the path, the circuit path from the brain to the periphery plays a significant role. Like, it's faster to retract your hand than your foot because the foot goes like further away than your hand.
No, I don't think. No, it's not. It doesn't depend on how far it is. Also, so for example, nociceptors, so the ones that receive pain in this, like the ones that just convey information about the pain, usually travel faster than something else, right? If you start putting like some pressure in your skin, yes, my brain is gonna be like, okay, there's some pressure. But if I start with pain at the beginning, like it will be like, so the same receptor is sensing pain. It's not gonna sense the pressure unless it's a pressure that it's being like, okay, no, now we are at the level of pain, and this information travels like this to the brain. So and how it happens, we saw the other time, I think we saw that there's some neurons that have myelin. So then it's just like this shield that is trying to convey this action potential and this message as fast as possible. So it depends on that, and not depends on how far are we from the yeah, so it's not about the length of the path going up and down, and you will feel more like you will feel something faster in your hand than in your feet. It's not like that.
There's another question. Does the monosynaptic stretch reflex circuit goes through the brain? And then it says it doesn't because the spinal cord is not part of the brain, right?
Yeah, no, okay. So when let's say the computation happens in the central nervous system. So that's where we have these two different things. So central nervous system is the brain with the spinal cord. So it does happen in the central nervous system. So you have to go inside and then have this pool of neurons doing some computation and coming out, but it does not reach the brain. Like it doesn't reach the brain itself. And, or let's say it doesn't reach the cortex. So in the cortex is where we have, and then we will see it's basically all the associations that you create based on that. It's more like a high level like interpretation of whatever happened. So it in the very like in the local circuits that will be at the level with the spinal cord is with the muscles for the reflex. They're just like having this computation. You don't need more about it. But of course, there's some information that travels all the way to the brain and tries to make sense of these, like, oh, what happened to me? I just kick, and then you start like, I don't know. Now, for example, you know that if you go to the doctor and they will hit you with the hammer, then you will kick. This is just because your brain at some point conveyed this information, and then you have it as a memory, and now you relate that, oh, whenever I see a doctor with a hammer, I know it's going to kick my knee, and my knee is going to be like this. And this is just your way to like, yeah, the message went all the way to the brain, and then you make sense of it. But the actual microcircuit just happening at the level of where the spinal cord is, and it's just like a quick computation, and it just goes back. So yeah, this happens in the central nervous system, but it doesn't happen in the brain. The actual reflex, it's happening because of circuits that are locally in the spinal cord. There's some more questions, I think. No? Okay. So this is, yeah, this is this drawing. So basically just fill in here that first comes the sensory neuron, then comes the motor neuron of the, what is this one, of the extensor, and then comes the muscle of the flexor. Yeah, so terminologies, okay, yeah. So we were just gonna upload
It's 11, just 11.
Oh yeah. So yeah, the definitions, I'm gonna upload them. So quickly, just to go through them, is just that this is the frontal lobe, this is the occipital lobe. Some people call it optical lobe. No, it's not called optical lobe. So the name is frontal, parietal, temporal, and occipital lobe. Yeah, the occipital lobe, it's mostly for vision, but it's called occipital. It's not optical lobe. So there's some questions about for example, the sulcus and the gyrus. So what is it? So, and this is just terminologies that you just need to know, because sometimes when people are talking about like, oh, these, like, I don't know, the primary somatosensory cortex is in like this with respect to the central sulcus and the postcentral gyrus, and then you don't know what this is about. It's just like our brain have all these folds, and then the kind of like the mountain thing is just like called gyrus, and then when it goes down it goes sulcus, and this is just a way to identify where the cortices are in the brain. We also have some like, what is the gray matter, the white matter. So the gray matter will be like all where there's the body, the cell bodies of the neurons, and the white matter is just the axons. And then why is it white? Is because of the myelin that it's shielding the axons. Yeah, so I don't know, like there's some of the definitions. I don't see a particular one that, so yeah, the definitions I will upload them all. I don't know if there's, yeah, if there's more questions, we can just have like, it's already 11, so we can just have questions on, I can just stay here until 11:10. What?
Question the forum.
Yeah, well, right now I can just offer that I can stay until 11:10 if there's more questions about this, and everyone else that wants to just leave, you can leave. And then yeah, after that we can just you can just post in the forum if you want to, yeah, if you have more questions. So this solution, which is this one here, will be available today. So I'm just going to upload it, so then you can just go through it, and then if there's something that's not clear, then you can just like you can just post it in the forum or send me an email. And also the exercise for the session today will be also uploaded the same way as we said last time. It will be a folder with the exercise number 3. And again, you are free to give the solutions or not. And yeah, also like I just advise, like, just if you have a question related to the exercise, which is makes it a bit easier for us, so you can solve the exercise and we will try to go through the responses. But maybe if you have a question specific, one of the exercises, just make me mark it or just put something that it's easier for us, so then we see how many people, oh, there was a lot of people having trouble with this question. So then that's the one that we try to focus during the exercise session, in case we don't have time to respond all the like to go through all the exercise. Yeah, I don't know. So are there questions?
There is one about inhibitory and excitatory neurons. I could not find a proper definition of them. I know inhibitory gives GABA, but no idea about excitatory. Definition of inhibitory and excitatory neurons.
Yeah, so basically, here we have it. Just a neuron that excites the postsynaptic neuron and increase the chances to have an action potential. So this will be here. So for example, here we have it. So if you see one neuron, so this is the postsynaptic neuron, right? And then you have connections from excitatory neuron and from inhibitory neuron. So what does it, what is like what we call excitatory? The excitatory neuron will be that this neuron fires, so has an action potential, releases neurotransmitters, and it starts to have an effect on the other neurons, right? So what happens is, depending on which channels this neuron, this neurotransmitter is opening in this specific neuron, you will either have an EPSP, so you will have like some increase in the membrane potential of the neuron, or you will have a decrease in the membrane potential of the neuron, right? And this depends exactly in the, as you mentioned, in the receptor. So the GABA receptors are gonna try to open the receptors for, like, I don't know, chloride, and then you're just gonna put the membrane potential down. So that's what we call an inhibitory neuron. An inhibitory neuron will be that still it fires, but the effect that has in the next neuron is inhibitory, saying it lowers its membrane potential. It is not trying to make it spike, it's trying to sink it, to not generate a response. So that's the definition of the neuron. The excitatory just has a positive, tries to bring the next neuron to spike, and then inhibitory tries to suppress the activity of the neuron.
What is association cortex?
Okay, let's go through the definition. So defined by exclusion as those neocortical regions that are not involved in primary sensor or motor processing. So as I said, like, our brain will be like, okay, so there's some heat, and it just goes, and then it just like conveys this information to the brain. Association cortex will be more like, what do we do with this stimulus? So I give you the example of, let's say, okay, so you know what a bird is because you know how a bird looks, how a bird sounds, and basically the definition of a bird itself, it's just something that came with association. So if you see it as only the stimulus that come, you're just outside and then you hear something, this is pressure, this comes inside, and then your brain is like, we hear these, there was these waves in like when you were sitting in the park, we sense this pressure in the air, and we just classify it, there's something here happening. But at the same time, your eyes were like, oh, there's some light change in the light intensity, and we identified this pattern. There was like kind of a circle and these, and then they had like a peak, like a triangle there. So yeah, okay, so we saved this here. And then, I don't know, also we saw that it was blue or whatever. So what the association cortex will do is like, okay, so this sound, we heard it, or this pressure in the air was at the same time as this light intensity. So this kind of shade does this kind of noise, and then you learn to call this a bird. So that will be the association cortex, are the ones that are not like, this cortex is not responding directly to the stimulus of the pressure of the air or the light intensity, just associating these different stimulus to create, like, to make sense of the world. Those are the association cortex. Yeah, that's it. Okay. I just see a number of 67 in the chat, so I get like super.
No, it's fine. I mean, there was no question.
As explain hyperpolarization, why and when this happens. Thank you.
Because it's already 8, 11, 8.
Yeah, no, but I said I will say until 10.
But
yeah.
still gonna have 2 minutes.
I don't think it was. Yeah, hyperpolarization is just like, so we have it here. I know it's not here. Yeah, so hyperpolarization will be with this B part, like a depolarization is when you increase the membrane potential of the postsynaptic neuron, and hyperpolarization is when you sink this membrane potential of the neuron. That will be, so an inhibitory neuron hyperpolarize, an excitatory neuron depolarize the next neuron. Okay, yeah, that's basically it. Yeah, I guess that's all. Okay, well, thank you everyone. Yeah, I'll post the thing, and then just as I said, please just maybe make a note if you have a question specific in the exercise, so then it's easier for us to look at it when we go through the solutions. Okay, have a good day.
Can I stop the recording?
Yep.